Okay, so for this class, I know you're all dying to think a lot about your heat transfer exam coming up. So we're not going to talk too much about it today, just sort of giving you guys the outline of it. So it is next Monday, a week from today, at this same time in this same place. It's going to cover chapters 1 through 5, so it's going to be focused on conduction. Although as you're learning with conduction, especially when you have to deal with an energy balance or something happening at a boundary, then you have to have sort of a rudimentary knowledge of convection at this point, which is basically Newton's law of cooling. So pretty much the things we've been covering so far are all going to be fair game for the exam. I'll provide an equation sheet for you, so I may modify it a little bit between now and Monday. I'll try to post a final version though, like by the end of this week. So tentative copies on Canvas now, just so you kind of know what to expect on the exam. You can also bring your own equation sheet. So that's going to be 1 page, front and back, no bigger than 8.5 by 11. It's going to be a closed book exam. That's sort of the norm, right? Do you guys are any of your exams open book? Every single one? Open book means your professor makes the exam much harder. And I've found, I tried open book my first time teaching, and it was not, even though you say you want open book, what you really want is a closed book exam and you to be the only one that can use the book, but I'm not doing that. So calculators are allowed, but absolutely no other electronic devices. This should go without saying. So definitely no computers or tablets or phones. And I'll patrol the classroom, and anyone violating that policy will probably get a 0 on the exam, which will make it really, really hard to pass the class. Yeah, Caleb? Yeah, that would fall under the no other electronic devices allowed. So no use of any watches or web-connected devices. Although I'd be really impressed if you somehow found a way. I guess you could text somebody. I don't know. Okay, so no watches. All right. So I've also posted old exams from the last 3 years on Canvas. So those make for pretty good practice problems. I think as you do them, some of the problems will look very familiar to you because some of those have found their way into your homeworks. So those exams are on Canvas. The solutions are also on there. The solutions tend to not be very explanatory, a little bit, but you can go see the solutions. I'm happy to answer questions about them. Okay, so that's pretty much it. Any other questions regarding the exam? Okay, so this is just the upcoming schedule. So today we're actually going to be getting into chapter 6, which is convection. I do want to point out that those 2 industry dinners are tonight from SWE and from AICHE. Are there any representatives from those organizations here? I don't know if they're still taking people, but if you're not signed up for one of those, I think you're really missing out. Those are really good opportunities to sit down and have one-on-one FaceTime with people from companies. So I believe at least SWE said they're still, yeah, they said they would even take people at the door. So, and AICHE, you probably want to scramble and get registered for it, but really good events. So if you remember, you don't have a homework from me this week because I want you to go to the career fair and really focus on that, and then the later half of the week you can use to study for your exam. So please use that time. I promise you, getting a 90 or an 80 on this exam is going to be pretty immaterial compared to job offers that you could get from the career fair. And I say that as a professor who wants you to study hard and get good grades, but those tiny little marginal differences in GPA are really nothing compared to having a resume that's rich and full and has a lot of good technical content. If you haven't heard me say this before, your GPA takes up like 1% of the space on your resume. And while it's important, you've still got to figure out what you're doing with that other 99% of the space. Okay, then Wednesday, we're going to get into chapter 7. Depending on how fast things go today, we may get a little bit into chapter 7 today. That is something called external flow with convection. So that's convection that's going around a surface where the flow isn't bounded by a pipe or a channel. Then on Friday, we're going to take a step back and cover some review for the exam. Next Monday is the actual exam. That's on the 30th. Then we get deeper into Chapter 7. The week after that, fall break. And then after fall break, this is going to be posted soon. Dr. Pershing, I don't know if you remember him from that first day of class. So he's actually the co-teacher of this class. So he's going to have a couple of really cool interactive lab things that you'll do. From last year, I think they were fairly easy for students. We just want to get you guys outside of lecture and computer and doing things with a pen and paper and see how things really work in reality. So he'll have a couple of interactive things. So that week, we'll have a sign-up sheet, and you'll get in groups of 2 or 3 and show up, and Dr. Pershing will be there. He's like the nicest guy in the world. He'll be there to kind of walk you through, and then there will be a little assignment combined with that. So I just want to get that on your radar. That'll be the week of October 14th to 18th. So that topic is more along the lines of external convection, and we'll be getting into internal convection at that point in Chapter 8 in class. Any questions about the schedule? Okay, raise your hand if you're planning on doing something related to the career fair this week. All right, not bad. Okay, so cool. Moving on. Okay, so actually one more thing. At the end of class on Friday, and by the way, the recording did not work Friday. This software that I use just hung up for like hours and I could not figure it out. So sorry, there's no YouTube lecture posted from Friday, but I've posted all the slides. At the end of the day, Friday, I used Socrative to ask you guys what you wanted to review for basically what will happen this coming Friday. Which topics do you want to review for class? So if you haven't responded to that, I'm going to close this here in about 20 minutes because I'll need to use Socrative for class today. So log into Socrative if you haven't responded to this. I'm going to go through and look at some of the topics. If there are like common things that no one is really getting and want me to review, then I'll try to tailor Friday's lecture toward specific things that'll be review. No guarantees because there's a lot of, as you can see, there's already a lot of different answers here. But I'll do my best to cover these common themes on Friday. Okay, so now we're moving on to Chapter 6. So these next few chapters, so Chapter 6 is sort of a basic introduction to convection. There's not really a ton of real meat in this chapter. I mean, there are some equations, but most of our focus will be on the later chapters. So chapters 6, 7, 8, 9, and 10 are all on convection. So the most important of those chapters would be 7 and 8, and then I'll cover 9 and 10 kind of a little more lightly, and chapter 6 is going to be a little lighter as well. Okay, so first of all, open question. So it's not a Socrative interactive question. So if you're standing in the middle of a very large flat field and you encounter hurricane force winds, there's no time to run for shelter, what would you do? Okay, drop. Okay, so why would you drop down to the ground? Okay, reducing your surface area, that's great. Anything else? Okay, great. Yeah, lower center of gravity, reduce your exposed surface area to wind. Okay, anything else? Joseph? Okay. All right, good answers. Okay, so one possible answer is that the speed of the wind is actually going to be lower closer to the ground surface. And that is because of something called a drag force. You guys are probably getting this in fluids, or maybe you just don't even want to mentally think about fluids right now. So today is we sort of cross over into fluids a little bit. I'm going to treat that stuff pretty lightly and let Dr. Zengel blow your mind with all the fluid stuff. So if everything were nice and ideal and the wind was just blowing in a single direction and there were nothing to block the wind from you, you would actually experience that the wind speed is going to be much lower closer to the ground. So while all of your answers were valid and probably really smart reasons, this is another reason that the wind speed is actually reduced. So when wind or when air or when water flow over a surface, there is a drag force between that very bottom layer of the fluid up against the solid, and so you actually get lower velocities closer to the solid. And then the higher up you go, the faster and faster that velocity gets. So really kind of a conceptual way to motivate you guys into thinking about boundary layers. Okay, so another question. So this one should be really easy now. So why are wind turbines so tall? Yeah, they're trying to take advantage of that faster wind that's further away from the surface of the ground. So here's an example. So the higher up you go, the better wind energy you'll be able to access because it's further away from the ground. There are less obstructions and obstacles. But even if it were wind flowing over a perfectly flat field, the wind speed would still be higher up because the ground itself, this flat ground, even with wind flowing exactly parallel to the ground, is going to cause a drag force that'll make the fluid flow more slowly toward the surface. So you can see this. These are real wind turbines that float in the air in the city of San Francisco. That's a little old. This is from the movie Big Hero 6, where they have these floating wind turbines to take advantage of that higher stuff. But it's not that far from reality. So there are really researchers doing this kind of thing and just seeing if they can take advantage of the better source of energy further and further away from the Earth's surface. Okay, so why are we talking about this? So these are fluids questions, and today is a really poor day to ask you guys about fluid stuff. However, everything we've been talking about so far in conduction, we've been dealing with a solid or a stationary fluid. So the fluid's not, if it is a fluid, which we haven't really talked about that much anyway, it's not moving, it's just sort of sitting there. So we've been able to solve the heat equation and get temperature profiles, and we've learned how to do energy balances. So now with convection, we're going to throw in this extra thing into the mix, and that is that the fluid, if we're talking about heat transfer from a surface to a fluid, that fluid is typically going to be moving in some way. So now we'll have to combine fluid flow with heat transfer and talk about those two things combined. I think you'll find, again, I'm going to leave most of the fluid stuff to Dr. Zengel, but we'll find areas where there's some overlap of the two subjects. So the things we'll be talking about are going to be at the intersection of heat transfer, fluids, and mass transfer. So we're going to be talking about something called a boundary layer. So have you guys gotten into that in fluids yet? Yeah, okay. So in fluids, there is something that forms called the velocity boundary layer. That's what we've been talking about. In heat transfer, there's going to be something called the thermal or temperature boundary layer. So that if there's heat transfer happening between a surface and the fluid, you won't just have a velocity boundary layer, you'll also have a temperature boundary layer. And then in mass transfer, which you'll get later, there is something called the concentration boundary layer. And mass transfer and heat transfer, those two topics are quite analogous. So I hope that some of the concepts and some of the math that you're doing here will help you to understand mass transfer better. Okay, so a boundary layer is a consequence of viscous effects. So that's those shear forces that happen between the fluid and the solid. And then each fluid is going to have viscous forces. Each layer of fluid, if I can put it that way, is going to have viscous forces against itself. So it's a consequence of viscous effects associated with relative motion between a fluid and a surface. So the boundary layer is a region of flow characterized by shear stresses and velocity gradients. And then it's also a region between the surface and the free stream whose thickness delta increases in the flow direction. So it's manifested by a shear stress that provides a drag force. So it's really kind of a mathematical thing that's done for mathematical convenience. So we define the velocity boundary layer being the point at which the fluid velocity is equal to 99% of the free stream velocity. So in theory, if we were to plot, if here's our x and here's our y. And if we were to plot our velocity on top of this thing, so theoretically, this thing would only asymptotically approach the free stream velocity. So the free stream velocity is like the bulk velocity that would happen in the absence of a surface. So here at the beginning, where x equals 0, we would have this free stream velocity, which is basically what's called plug flow. All the flow is just coming uniformly. Then when it encounters that surface here at x equals 0, those drag forces happen. So those drag forces first just affect that very bottom layer of the flow, but as the flow continues down our surface, those drag forces propagate up through the flow. So theoretically, we never really approach the free stream velocity, but in actuality you would, and you'd get things like turbulence that are going to make this a lot messier. So the thing to remember is this delta is defined as our x velocity as a function of y relative to the free stream velocity, u infinity, or I'll sometimes call that the bulk velocity. So as soon as our u as a function of y is 99% of the bulk velocity, that's where we define the height of our boundary layer. Okay, so let's change this up a little bit. Before I go into that slide, so imagine that that this table here it's heated. Imagine it's a stovetop or something, and it's just uniformly heated all along the way. So I come over here, and I take a big fan, and I blow that fan again across the surface of the table. So what's going to happen to the air? So if I'm holding the fan here, maybe a few feet away from the table, and it's a really big fan with a big cross-sectional area, let's suppose that I can create this really nice uniform flow. So that flow is going to be coming at a u infinity, all at a nice uniform flow. Then when it encounters the table, what's going to happen in terms of the velocity profile of our flow? So so if it's just this nice uniform flow, before it hits the table, it'll be nice and uniform. So it'll be constant with respect to y, which would be the distance from the height of the table. So as soon as it encounters that, what's called the leading edge of the table, that the flow is going to start experiencing the viscous forces caused by the table. So we'll start to see a boundary layer form. So our flow, initially the very bottom, quote unquote, layer of fluid will encounter the table, and it'll be dragged down by the table. And so as it moves along, that bottom layer of fluid is going to grab onto the layer immediately above it. And so in terms of velocity, we'll start to see the formation of a velocity boundary layer. So just back to the wind example, if you were to put your hand directly on the table, you wouldn't feel as much velocity in the wind as if you put your hand up here. So you could probably do that just by sort of visual and tangible inspection. You would experience a higher velocity further away from the table because of this formation of a boundary layer. In my example, I said that the table was heated, so we have some sort of flux that's heating this table. So what's going to happen is that bottom layer is going to start being heated. So if you remember, as we've talked about convection up to this point, we've just treated convection as being totally uniform over the whole surface. But what will really happen is the convection will change as that boundary layer grows. That boundary layer will serve as sort of a barrier to heat transfer in some ways. And so as that boundary layer forms, the rate of heat transfer, depending on your x equals 0 or x equals L, could be physically different. So in addition to this velocity boundary layer forming, we're also going to get something called a thermal boundary layer that forms. So the thermal boundary layer, so from the fluids example, you add in these thermal effects and it gets a little bit more complicated. So the thermal boundary layer is a consequence of heat transfer between the surface and fluid. So it's a region of flow characterized by temperature gradients and heat fluxes. So it's a region between the surface and the free stream whose thickness, delta sub T, increases in the flow direction. So it's manifested by a surface heat flux and a convection heat transfer coefficient. So similar to the velocity boundary layer, the thermal boundary layer, it's also defined by delta, only now we have that little subscript T on there. So delta sub T is our thermal boundary layer. So that is defined as the point of which our temperature in the y direction, so is 99% of the way between our surface temperature and T infinity. So in that particular example, if we have a hot surface and we're blowing this cold air over the top of it, we would physically see a temperature profile develop like this, where the temperature is going to get cooler and cooler the closer you get up to here, right? So let's go back to our thought experiment. If I'm blowing a fan over this hot surface, if you hold your hand really close to the surface, it's going to feel warmer, but the further away you get from the surface, it's going to feel cooler and cooler. So prior to this, we've treated convection mathematically as just a sudden jump in temperature between a surface and the bulk fluid, but really there's a boundary layer that forms there. So mathematically, it's convenient to use Newton's law of cooling, and we'll continue to do that, but realistically, there's going to be this sudden temperature drop-off. Any questions there? Is anyone confused by this? Still just reeling from fluids exam? That's all right. So prior to this, when we've looked at a plane wall, and if we draw the temperature profile, let's say this is x and this is temperature, we know that if this is a steady state, the temperature profile through a plane wall will just be straight. So mathematically, the way we've treated this is sort of as a sudden jump in temperature from the surface of the wall out into the bulk, and similarly for up here. But in reality, there's going to be this fluid motion happening on both sides, and so we would expect to see, and you've seen this in some of the plots, but we haven't actually dealt with it, you'd expect to see really something like this that happens, and our air temperature sort of exponentially approaches the bulk surface temperature. But a lot of assumptions have gone into this type of analysis. So one of those assumptions is that everything on the air side is just perfectly well mixed, and that is a big assumption. It's valid and reasonable in a lot of cases, but in some cases it's not, that there is actually a spatial component to temperature, even dealing with convection in a fluid. Okay, so to this point, we have treated convection as happening uniformly over the surface due to bulk fluid motion with all the fluid at the same temperature, and we've also assumed that H, our convective heat transfer coefficient, is just constant. So it's shown as a continuous temperature profile from surface to bulk. So there really are spatial effects. There are lots of other effects. So H can be dependent on a whole variety of other factors, including how dense or how fast the fluid is flowing, what the surface dimensions are, if that surface is rough or if it's smooth, and then characteristics of the fluid itself, like the viscosity, density, conductivity, and there are still others. So one of those that I neglected to include on here would be like surface geometry. So a surface energy balance would actually show that the convective coefficient is dependent on the thermal conductivity of the fluid itself. So like in that plane wall system, remember that our flux as a function of x going from some point here in this room to some point in the other room, the flux remains constant. So even here, if we're looking at a macro view of things, even here in that boundary layer, we would still expect our flux to be constant, which would allow us to do something like this guy, which is basically based on an energy balance, saying that, and if you rearrange the terms, you would see Newton's law of cooling, so the convective heat flux is basically equal to Fourier's law of conduction, except now we're talking about conduction through the fluid itself. And the K, notice that K sub F, that K is characteristic of the fluid's thermal conductivity. So I wouldn't worry too much about this. But when a fluid is circulating, you would still expect a fluid with a higher thermal conductivity to have a higher convection coefficient than a fluid with a lower thermal conductivity. So those kind of fluid properties will greatly influence the value of the convective heat transfer coefficient. So in addition to the convective heat transfer coefficient being dependent on thermal properties of the fluid, it could actually be, there's a difference between a local heat transfer coefficient and a global or average heat transfer coefficient. So the local heat flux and temperature can actually vary. So if you think back to that example, if I have a really hot surface here and I'm blowing air across, you would expect the temperature in the air to sort of change as the further you go down. The air has had longer time to heat up as it goes from x equals 0 down to x equal L. So that tells us we got to start factoring in spatial dependencies. So one thing that's going to be a really important thing to understand is that you can have a local heat transfer coefficient, which you can state basically that the flux at any particular point is characterized by Newton's law of cooling, h times Ts minus T infinity. But because that h may change, your flux may change depending on where you are on the surface. And the formation of that boundary layer will influence what's happening. And we'll get into correlations to help us describe what the local heat transfer coefficient is and or what the average heat transfer coefficient is. So back to this table example, we're going to expect a boundary layer to gradually form as the fluid flows across this table. So as that boundary layer changes in thickness, we're going to expect our heat transfer coefficient to change because the fluid flow properties have changed over the course of over the length of the table. So if we wanted to get an average heat transfer coefficient, we could do that by integrating the local heat transfer coefficient over the entire length of the plate. So when you see in convection, typically when you see this H just raw by itself, that denotes a local heat flux. And then when you see it with a bar over it, oh, I misspoke, sorry. When you see the H that's just raw, that denotes a local heat transfer coefficient. And then when you see it with a bar over the top, that denotes an average heat transfer coefficient over the entire surface. So depending on what information we want, maybe we want to know surface temperature as a function of x, then we would want to deal with this local heat transfer coefficient and actually come up with a relationship that describes our surface temperature as a function of x. But if we wanted to just treat the whole thing as being uniform, then we could deal with an average heat transfer coefficient. And the way to go from a local to an average would be to do this integration. So here you integrate the local heat transfer coefficient multiplied by a differential surface area that's experienced as you travel down the length of your flat plate. And then you multiply that whole thing by 1 over the total surface area, and that would give you an average heat transfer coefficient. So for a flat plate in parallel flow, if we had some correlation giving us h as a function of x, we could integrate that correlation over the entire length and come up with an average heat transfer coefficient. So we've got an example here. So this one's from the book. So suppose that someone did an experiment and they actually tried to calculate what the local heat transfer coefficient was and put a correlation to it. So experimental results for the local heat transfer coefficient h sub x for flow over a flat plate with an extremely rough surface were found to fit the relation h as a function of x is equal to a times x to the minus 0.1, where a is a coefficient. This is just someone did an experiment and they used Excel or whatever to fit a relationship to that. So how would we go about finding the average heat transfer coefficient over the whole plate? We would just apply that equation. Sorry. So we would apply that equation where we would get the average H is equal to 1 over L times the integral of 0 to L times H x dx. So we would just substitute in our relationship here into this equation. So that would equal 1 over L times the integral from 0 to L of ax to the minus 0.1 dx. So doing that integration, we end up with a over L multiplied by L to the 0.9 divided by 0.9, which is also equal to 1.11 times A times L to the minus 0.1. So this is the way you would translate a local heat transfer coefficient into an average heat transfer coefficient over a specified length. So you'll notice the local heat transfer coefficient is a function of x. So H is going to vary depending on where you are. But if you just want to look at the whole flat plate or the whole table and figure out what the average is, then you just get this. And every term in here is just a constant. So A is a constant, L is a constant, and then this 1.11 certainly is a constant. Any questions there? So convection is going to get a little bit more complex than we've been treating it so far. We're going to be dealing typically with a lot of correlations that'll be more complex than that relationship. There's some really nice theoretical stuff in here, and there's some really interesting stuff that'll certainly be important for you throughout your careers. But then there's a lot of these messy correlations that are based on somebody's like very, very detailed analytical solution or somebody's series of experiments that they did. So a lot of the times we'll just be looking at, for that particular instance and that geometry, here's a correlation that applies. So a lot of convection is going to be figuring out the right correlation to map, to match your circumstances so you know how to calculate H. So here's how those results would look plotted. So if I were blowing air over a heated surface, at the beginning, based on that particular correlation, we would see a higher heat transfer coefficient, and then it would gradually decay and become lower. But if we wanted to look at the average, again, an average is just an average, so the average from 0 meters to 4 meters would look like that. However, if we wanted to take a different average from 0 to 10 meters, then because our local coefficient keeps on decaying the further out you go, gradually our average would also decay. So the average is somewhat arbitrary depending on where you're taking an average from where to where. So just note when you're taking this average, you're really doing a rough approximation because maybe you don't care about all the nitty-gritty details of how H varies with X. Any questions so far? Okay, so this is going to be something that is a little bit different. So from your fluids class, don't look at this slide yet. Well, okay. This has nothing to do with this slide, let me say that. From your fluids class, what is the Reynolds number at which flow transitions from laminar to turbulent? 2,400? Okay. So that is a number that will certainly apply to this class, but that number is dependent on fluid. That's basically for a certain instance. So the Reynolds number is still going to be really important in this class, but there are going to be different geometries. And so mostly by empirical results, I think they found that depending on your geometry, that the Reynolds number at which you transition from laminar to turbulent may be totally different. So thinking about just fluid flow over a flat plate, what's going to happen is that we've described a boundary layer, so that fluid will encounter this leading edge. That fluid on the very bottom, quote-unquote, layer of the fluid is going to start grabbing onto the surface of the table. It's going to go slower, which means it's going to slow down. Those viscous forces are going to slow down the layer just above it, and that fluid is going to slow down the layer just above it. So this boundary layer is going to keep on growing and growing until it gets to a point where it's too big to maintain laminar flow. And once it gets so big, some of that fluid's going to start circling back, and it's going to create these eddies, and the flow is going to transition to turbulent. So at some point, once the flow, and again, keep in mind this is all very theoretical and under really ideal circumstances, but at some point, that flow is going to transition to being turbulent flow. So one thing to keep in mind is that unlike in your fluids class, when you have that particular number in mind, when you have flow over a flat plate, your Reynolds number is going to be calculated differently. So here, for flow over a flat plate, the Reynolds number is calculated like this. So the Reynolds number is rho times the bulk velocity times x over mu, where mu is still, that form should look pretty similar, right? Whereas flow in a pipe is going to be rho VD over mu. We have basically all those same terms, except there's one really different term. Instead of a pipe diameter, now you've got x. So what is x in this conceptual example that I keep alluding to of flowing over a flat plate? Okay. And let's get rid of this little c for now. Just x. So the way we defined it, x would be the distance you are from the leading edge of the flat plate. So really the important thing to remember here is x is a variable. It's not a constant. So typically when you're talking about fully developed flow in a pipe, you're using just the pipe diameter. So your Reynolds number, once the flow is, well, I guess always, your Reynolds number is the same thing because your pipe diameter is the same all the way through. However, now Reynolds number is a function of x. So your Reynolds number is actually growing and growing the further you are away from your leading edge. So that, it sounds simple, that kind of fundamental thing is going to be important to remember as we talk about external flow. So this x sub c is a specific location at which the transition to turbulence begins. So at some point, the flow is going to become turbulent. So for flow over a flat plate, that critical Reynolds number is typically 10 to the 5th. So it's 100,000. So that's very different than the 2,000 that you're used to, because this Reynolds number is describing flow over a flat plate. It's not describing fully developed flow through a pipe. Any questions there? So just kind of a fundamental thing to keep in mind. This is just a totally different geometry. So our Reynolds number is defined differently, and the point at which we transition from laminar to turbulent is different. And there's actually a physical transition. So let's say that the critical Reynolds number happened halfway through. That means prior to the flow reaching that critical point, it's going to be laminar. And then after that, it's going to be turbulent. So even for the same physical system at steady state, you could have one region of your system that's laminar and another region that is turbulent. And that's going to drastically affect the heat transfer characteristics. Okay, so I'm going to launch this question real quick. So the question is, let's just digest this and think about it, and then I'll go launch the question. So for this system, where on this plate do you expect to see the highest local convective heat transfer coefficient? Okay, so now you can actually answer it. So here are the choices. You can hopefully see a better picture on this device. So where do you expect to see the highest local convective heat transfer coefficient? At x equals 0 on the far left end, because the boundary layer is the thinnest there. At the end of the laminar region, when the boundary layer is thicker and before it transitions to turbulent. C in the transition region, D at the beginning of the turbulent region, or E at x equals L, the far right end in the turbulent region, because the fluid has the best mixing there. So just to totally use your intuition, where do you think you'll see the highest local convective heat transfer coefficient. And remember Newton's law of cooling had its H times Ts minus T infinity. So you're trying to get heat from the surface temperature out to the bulk, if that helps at all. All right. So this one is kind of, I actually put in a right answer, which it's really kind of subjective, so this could vary. So at the beginning of the turbulent region. So one thing to keep in mind, so there are a couple of competing forces here. So you want the thickness, you want the boundary layer to be really thin, so there's less physical distance between the surface and the bulk fluid. But turbulence itself is a really good way of mixing things up and helping heat get transferred quicker. So that turbulence is really going to help you mix the fluid up better and convey it away from the surface out into the bulk, because it's going to have those eddies. It's going to be swirling and circling and helping to move heat better. So hey, wow, you guys are doing much better now that we showed the right answer. Okay. So there is some ambiguity in here, though. So if we were to plot a correlation, again, this is sort of rough, you would see this is how our heat transfer coefficient changes with respect to x. So it's certainly higher at the beginning of the laminar region where that layer is thin, but that as the boundary layer builds and builds and builds, is creating more physical distance between our surface and the bulk. So our heat transfer coefficient, because of that extra thickness, it starts to degrade. Then suddenly, when we transition from laminar to turbulent, we suddenly get this much better transfer of heat, because that turbulence really helps heat to be transferred faster. So that combination of our boundary layer being relatively thin, plus all the circling and swirling that's happening due to turbulence, creates the highest heat transfer coefficient. And then once you've got turbulence and the boundary layer keeps on growing, then your heat transfer coefficient starts to degrade again. Any questions here? It's all sort of just conceptual. So in this class, I'm glad that you're already getting familiar with the Reynolds number, because we'll be using the Reynolds number in a lot of these convective heat transfer correlations that I alluded to. So we're going to need to know what the Reynolds number is. It's that same form, rho v some dimension over mu, except for that dimension. So I have it here as L. It depends on your geometry. That might, in some cases, when we're talking about internal convection, that's going to be the inner diameter of our pipe. But when it's flow over a flat plate, that's going to be X, which means our Reynolds number is going to be different depending on where we are on the plate. We're also going to be talking about something called the Prandtl number, which is more a characteristic of the fluid, and it has something to do with the viscosity relative to the thermal diffusivity. So the Prandtl number is the ratio of basically the momentum diffusivity to the thermal diffusivity. We are also going to talk about something called the Nusselt number, which is going to be defined as HL over K. This is very different from the BO number. So remember, the BO number told us something about how fast, well, since you guys are studying for the exam, what's the BO number? What do you use that for? Okay. So the BO number tells us something about how fast convection at the boundary of a solid, how fast heat transfer happens with convection relative to how fast heat happens with conduction in the solid. Whereas the Nusselt number is only about the fluid, and notice it has this K sub F. So while it looks mathematically similar to the BO number, it's a different thing. So typically, the Nusselt number is basically a dimensionless heat transfer coefficient. So people will do experiments, and they'll try to figure out, okay, what specific velocities and geometric configurations lead to a certain heat transfer coefficient. they want their experiments to be fairly ubiquitous and to apply to a general case of any fluid. So they'll typically generate these correlations that give you a Nusselt number, and then from the Nusselt number you go and figure out what your actual H is for that fluid. And we'll get into that. So the Nusselt number is going to be very important. So it's going to be typically a function of our geometry, a function of our fluid flow, and then function of the fluid itself with the Prandtl number. So we'll go through this general procedure that you'll get very familiar with. So the general procedure for finding our local, or our convective heat transfer coefficient, whether that's local or average. First, we're going to find the Reynolds number and the Prandtl number. Then we're going to look up the right correlation to find our Nusselt number. And then we're going to back calculate to get H by undoing that relationship and saying that H is equal to our Nusselt number, and this should be a little k, times the thermal conductivity over L, where L is some characteristic dimension. Yeah, Nimdo?
Is the L in the Nusselt number characteristic length?
Yes. Mm-hmm.
KF, I'm kind of confused.
Okay, so sub F means we're dealing with the thermal conductivity of the fluid. We're talking about convection anymore, so we're no longer going to care as much about, at least when we're talking about convection, about the thermal conductivity of a solid. Now it's going to be all about the fluid. So H is going to be a function of what's happening with the fluid, and much less, we won't care nearly as much about what's happening in a solid that it interacts with.
And the asterisk, does it mean that those are like changing depending on,
Yeah, the asterisk on the X just means, I think I pulled this specific relationship, but it's basically going to be, that's where our dimensional thing goes. So we might have flow like around a cylinder or around a sphere or over a flat plate or through a pipe. So that the space and the geometry will vary, and our correlation will change depending on what our geometry looks like. This will make much more sense once we start getting into specifics. Okay, that is the end of chapter 6. We're about 3 minutes early, so I think we'll just leave early. So we'll get into chapter 7 on Wednesday, and we'll get into more specifics about how to apply this methodology. So that's just sort of a conceptual introduction to convection.